Okay, good morning, students. So, welcome back to the GATE training program. So, in previous session, we discussed about finite automata and regular languages and regular expressions, etc. So, today's class, we are going to discuss about push-down automata. So, this is the next level of model in theory of computation. So, the basic model is finite automata. In that, we have two different types, non-deterministic finite automata and deterministic finite automata. So, we have one drawback in finite automata, right? Because there is no memory. We cannot store anything in finite state machine. So what is finite state machine? It is nothing but the other name of our finite automata. So due to that, we go for the next higher level, that is push down automata. Okay, so see the name here, push down automata. So push is nothing but the operation of our stack. So in this push down automata, we are going to introduce one small memory unit, which is nothing but the stack. Okay, so we can store some limited amount of symbols in this stack. So what is symbol? It is a basic building block of our finite automata or push down automata. Any model, symbol is the basic building blocks. Okay. And then we should remember the basic concepts here. Okay, so what are all the basic concepts? So first, what is alphabet? Alphabet is nothing but the set of symbols. Okay, it may be a numbers, numerical value from 0 to 9, or small a to z, capital A to z, otherwise any special character, plus, minus, star, slash, etc. These are all the alphabets. So alphabet means it is a set of symbols, and then using these alphabet we can construct the word. What is word? It is nothing but the collection of alphabets. Collection of alphabets is known as the word. The other name of word is a string. Okay, and then what about language? So language is nothing but the collection of strings over the alphabet. Okay, so L is used to represent the language. Capital L is used to represent the language. And then we have a sigma symbol, that is summation symbol, which is used to represent the alphabet. And then what about small w, which is used for our string or word. So these are all the basic concepts of any automata. It may be a finite automata or push down automata or Turing machine. These are all the basic concepts. That is what is alphabet, what is symbol, what is string, or what are all the languages. So these are all the basic concepts. Now coming to the push down automata, here we are going to overcome the drawback of our finite automata, which means we are going to introduce a memory here. So which type of memory? We are going to introduce a stack alone. So stack means we can perform the operation. What are all the operations can be performed on the stack? That is push or pop operation. Push and pop, those are all the operations on stack. Okay. And then coming to PDA, so here, what about FA? Its equivalent language is regular languages. We already discussed in previous session. No? Finite automata, it is a mathematical model which accepts the regular languages. Okay, regular languages, we have three kinds of operation, that is union operation, concatenation, and then the closure operation. Okay, so coming to the PDA, push down automata, its equivalent language is context free languages. Okay, CFL means which is context free languages. Okay, so in this context free language, we are using context free grammar. So what is grammar? It is nothing but the set of rules. Okay, these set of rules are used to construct the context free languages. Okay, and then what is PDA? It is a model which accepts the context free languages. Okay, we have two different kinds of representation in PDA, that is transition diagrammatical representation. Okay, so after that we have to write the transition function representation. Here we are not using the table representation, rows and columns, like our finite automata. Okay, so coming to PDA, this is equivalent to ENFA plus stack. Okay, so what is ENFA? epsilon non-deterministic finite automata with epsilon transition. That is called as the ENFA here. So PDA is the combination of ENFA plus stack. Okay, therefore the PDA it accepts the null string also. And then coming to the stack, why we are using stack here? We are giving some input to ENFA. Okay, we need to store some value to check whether the strings are accepted or rejected. For this, we need to store something in our memory. For this purpose, we are using stack here. And then what about the output? Whether the string, given input string is accepted or not. That is the output of this PDA. Okay, is it clear, Pa? So PDA means what? Finite automata, non-deterministic finite automata with E transition plus we are including one small memory as stack. Okay, and then move on to the next one. So this is the basic definition, that is formal definition of PDA. Okay, we already know that the formal definition of finite automata. It may be a DFA or NFA. We are using the same set of 5 parameters. So only change in our transition function alone. But here we have to include the stack. In formal definition itself, we have to include the stack here. So see, we have 7 parameters here. The first one is capital Q. Capital Q, we already know that the set of states, finite set of states. Okay. And then the next one is the input alphabet. And then third one is nothing but the stack symbol. Okay. This is for the new parameter in push down automata. Okay, well, we don't have this particular parameter in finite automata. So this is the stack symbol. The third parameter is the stack symbol. Okay, and then coming to the fourth parameter, this is the transition function. We already know this. We used this in our finite automata. And then Q0 is the initial state. Capital F is the final state. And then here we are using one more parameter, Z0. So Z0, it indicates it indicates the empty stack. Okay, it indicates the empty stack. And then the third parameter is the stack symbol. And then the sixth parameter is the empty stack. Okay, my initial stack or top of the stack one. That is, it indicates the empty stack. So totally we have 7 parameters in PDA. Finite set of states, and then finite set of input alphabet, and then stack symbol. We have transition function, Q0 start state, and then the initial the empty stack or top of the stack, and then capital F is the final state. So here in transition function, no, we have one extra parameter here. Okay, wow. So see here, this is the transition function. Here we have one extra parameter, that is the third parameter. In finite automata, no, we are using a current state and current input symbol. So based on this current state and current input symbol, we will decide the next state. Okay, but here you have to include the stack symbol. You have to include the top of the stack value in our transition function. We have to take the decision based on the current state, current input symbol, and then the top of the stack. So based on these 3 parameters, we have to decide the next state. So don't forget, in finite automata, we are using 2 parameters for transition function. Here we are using 3 parameters. We have to include one extra parameter here, which is nothing but the top of the stack value. Okay, so coming to the output of the transition function. So what is output here? Capital Q, which is nothing but the next state. And then we have to write the top of the stack also. Whether you are push something into the stack or pop out something from the stack, now you have to mention that also in our output. So here we have 2 different outputs. Okay, Q's is the state, current state, and then current summation, that is input symbol, and then third one is the top of the stack. So based on these 3 parameters, we have to decide the output value of this transition function. Okay, so see here, example transition of
small q comma a comma x. So here what is small q, which is nothing but the current state. A is the current input symbol, and then x is the top of the stack symbol. Okay, well, here we have to mention all these three parameters: current state, current input symbol, and then top of the stack value. Okay, well, it will give the next state. So here P is nothing but the next state, and then Y is at top, again top of the stack after performing push or pop operation. Here you have to mention the top of the stack also in our output of transition function. Is it clear?
Yes, don't forget here transition function, it accepts three parameters as a input and then it generates two parameters as a output. Okay.
So see here, P is the current state, A is the current input symbol, and then we have to refer the top of the stack. So according these three values, we have to decide the next state. So here, which is the next state? P is the next state. If the top of the stack is a non-terminal, we have to replace it with some terminal values. Then only we can perform the operation on PDA. Okay, see here, y equal to epsilon means you just pop out the top of the stack. That is the action. What is y? It is a current symbol. Okay, and then we have x on the top of the stack. Now, if it is the symbol is epsilon and then top of the stack is x, now you just pop it out. Okay, and then what about x? If the current input symbol y equal to x means, so directly pop out the x value or push the x value into the stack. Okay, and then what the y value is z1, z2, which is nothing but the collection of symbols. So what is collection of symbols? The other name of collection of symbol is our string. Okay, ma'am. If y equal to, if the string equal to a collection of characters or collection of alphabets, we instead pop out the y, that is the first operation. So instead of y, you have to push all the symbols, z1, z2 up to zk, you have to push all the symbols into the stack. Okay, while performing the push operation, you have to push the symbols from right to left. So right to left means what? First you have to push ZK, and then the second you have to push ZK minus 1, and then ZK minus 2, etc. and then Z2, Z1. So in this direction only you have to push the symbols into the stack in PDA. Okay. Right to left, don't forget, this is one of the important point in PDA. While inserting, while pushing the value, pushing the string or more than one symbols into the stack means you have to push from right to left. Okay. So coming to the example here,
We already studied about a pumping lemma, no? So pumping lemma, which is used to prove certain languages are not regular languages. Okay, well, so for not regular languages, we cannot construct any finite automata. So we cannot write its equivalent regular expressions also. Okay, these are all the non-regular languages. For those type of languages, we can design PDA, that is push down automata here. So let's see the example. Here the capital L means what? It is a language. W per R means what? The string followed by the reverse of the string. Okay. And then where W is in the alphabet is 0 plus 1 whole star. So here what is W, which is the word? It is a collection of symbols, zeros and ones. It is a collection of symbols, zeros and ones. And then the first half of the string, and then what about the second half? It is nothing but the reverse of the string, that is the given language. Okay, so in this type of language, no, we cannot draw the finite automata because we need to remember something. Okay, then only we can check the reverse of the particular string also. Okay, if you want to check the reverse means we need to store the string, then only we can check whether the second of is reverse of the first of. Okay, but in finite automata, no, we don't have any memory unit, so that we cannot store anything. That's why this is a non-regular language. In this type of language, we move on to the next higher level model, that is PDA, push down automata. So in push down automata, we are using a small memory unit which is stack. Okay, so this is the language. And then see, this is its equivalent grammar, CFG. Okay, CFG means it is a context-free grammar. Context-free grammar means we have some set of rules which is used to represent the language. So this is the equivalent CFG for the given language L equal to W per R. So capital S here is nothing but the start symbol, and then we have one arrow symbol, 0 capital S 0, otherwise 1 capital S 1, otherwise epsilon. So this is the equivalent CFG for the given language. So here what is S? It is a non-terminal. And then what about 0, 1 and epsilon? These three symbols are the terminal symbols. Okay, ma'am. So in basic concepts of CFG, we discussed all those things, that is terminals, what is non-terminal, what is vertices, that is, and then non-terminals, vertices start symbol. Okay, and then what about G is nothing but the grammar or set of rules. So here we have the rule for this particular language. So see the first one, capital S into 0 S 0. So first is the string, and then after S is the reverse of the string. Okay, well, what is the reverse of 0? It is 0 alone. Okay, and then coming to the second rule, capital S tends to 1 S1. Here also the same thing, that is 1 is the string, and then reverse of 1 is 1. Okay, and then epsilon, we can include the null string here. Am I clear? What is CFG? And then this is its equivalent to PDA. So we know that the PDA has 7 tuples. Capital Q set of states, and then alphabet. We know that 0, 1 is the alphabet. And then we have the stack symbol. In stack symbol, no, we have to include all the alphabets plus Z0. What is Z0? It indicates the top of the stack or empty stack. And then the fourth one, we have transition function. Q0 is the initial state, Z0 is the top of the stack, and then F is the final state. Okay. So in this example, that is W per R, we have three states. Q0, Q1, Q2. So totally we have three states. And then alphabet, we know that is 0, 1. And then stack symbol 0, 1 is at 0. We have a transition function here. Q0 is the initial state. We know that Z0 is the top of the stack, and then Q2 is the final state here. And then see, so this is the initial representation. So initially, one arrow followed by one circle means which indicates the start symbol or start state, initial state or start state. And then see the stack. Initially, the stack is empty. So Z0 is used to represent the empty stack or top of the stack. Okay, this is the initial condition of our PDA. This is the for transition diagrammatical representation. So transition diagram means we know that it consists of set of states and edges. That is, we are using a directed graph for drawing the transition diagram here. So one arrow followed by one circle. It is a initial state or start state. Initially, we don't have any symbol in our stack. No, that is, we are not performing any push or pop operation initially. So that is at 0, which indicates the top of the stack or empty stack here. So here, these are all the transition function. As I told earlier, we have two different representation of PDA. One is transition diagrammatical representation, and then second one is the transition function representation. Okay, so here we don't have. Here we don't have transition table representation. So see, the given language is the string and then followed by the reverse of the string. For this, first you have to perform the push operation. Push operation means the first half of the given string is pushed into the stack. Okay. The first symbol, so see here in the first transition function, there is transition of
Q0, comma 0, comma Z0. So this is the initial condition. See the diagram, Q0 is the initial state, and then current input, it may be 0 or 1. The particular string, it may starts with 0 or it may starts with 1. So for that, you have to write two different transition functions. The first one for the string, which starts with 0, and then the second string, which starts with the input symbol 1 here. Okay, and then what about the third parameter? You have to write the top of the stack symbol here. Okay, so initially we don't have any symbol, no, that's why you have to write Z0 here. So based on these three parameters, you have to write the output of our transition function. That is Q0 is the initial state, 0 is the current input symbol, and Z0 is the top of the stack. Then we are going to perform the push operation. Okay, that is we are going to push the value 0 into the stack here. Q0 is the next state. So Q0 is the current state, and the next statement part we are going to form an internal loop. Okay, start state Q0, and then draw one edge to the same state itself. So that is the internal loop. So the next state is also a Q0, and then what about the stack value here? 0 is at 0. Now 0 is the top of the stack. Okay, likewise, writing the same function for the input starts with 1 also. That is transition of Q0, comma, my string starts with 1, and then Z0 is the initial value of stack, that is top of the stack. So based on this, I can decide the next state. Here also, I'm using an internal loop so that the next state is Q0, comma, I am going to perform the push operation 1Z0. So this is the initial step. This is the initial step of a PDA construction. So coming to the second symbol. So first symbol over. So what is a string? It is a collection of symbols, no? So first two transition functions for the first symbol of our string. Okay. The first one, which is the string, starts with 0, and then the second one, the string starts with 1. So coming to the second symbol of the given string, okay, it may be 0 or 1, whatever it is, the second symbol, it may be 0 or 1. So first you have to write the transition function for the symbol 0, that is second symbol, and then you have to write it for 1. So see, Q0 is the current state, and then 0 is the current input value. Top of the stack is 0, means what? You are going to push the 0 into the stack. Okay. So here we mentioned only top two symbols alone. So no need to mention the whole stack here. So only you can mention the top two values from the stack here. So already we have 0 in the top. So currently we are going to push one more 0 into the stack here. If the current input is 0, but the top of the stack is 1, means what? I'm going to push the 0 into the stack so that the output is Q0, comma 0, comma 1, 0, 1. So same for our input 1. Okay. So this is for the second symbol. From 3 to 6, no, these four functions for the second and further second, third, fourth, etc. These input symbols, we can use the same transition function here. And then coming to the seventh one, okay, here we are going to check the top of the stack. Okay, if it is epsilon, current input symbol is epsilon, top of the stack is 0, then no need to perform any operation. If it is epsilon, top of the stack is 1, again no need to perform the operation here. In ninth one also, if it is epsilon and then Z0, we can stop the process because we reached the empty stack as well as the final state here. So this is the construction of PDA for the language LWW per R. Okay, see here state diagram or transition diagram representation. That is circle, which is state. Okay, and then we have one edge from one state to another state. It is a directed edge. We have to label the edge also. We are using three values in edges. Okay, the first value is a input symbol. And then second value is the stack value, and then the third is the stack top replacement. So based on this, that is current state and then the current input symbol, it gives the next state as well as the top of the stack as the output. This is the transition diagram representation of PDE. And then this is the general representation. So now we have to draw the transition diagram for the language L equal to W bar R. So as we know that the set of states Q0, Q1, Q2, and then we know the symbol 0, 1, and then we know the stack values Z0, 0, 1. You have to draw the transition diagram. So in transition function representation, no, we are using the self loop, that is internal loop, no. So that's why I'm writing all those things in the same places. That is, if it is 0 on top of the stack is at 0, you have to push it to the stack. If it is 1 top of the stack is at 0, then you have to push 1 is at 0. If it is 0, 0, you have to push 0. Likewise, you have to write the transition function here, that is values here. And then we have one more edge from Q0 to Q1 with the input symbols epsilon. Okay. And then again, we have one internal loop here in Q1 state 1, 1. If current symbol 1, top of the stack 1, you just pop it out. Current symbol 0, top of the stack 0, you just pop it out the top of the stack. So finally, you will be getting epsilon. Epsilon means what? This is a null string. Otherwise, it indicates the end of the string also. Okay. Epsilon means null string, which is used to indicate the end of the string. And then top of the stack is Z0. So what is Z0? Which indicates the empty stack. Okay. So reaching the final so there is no more input in string and then no more symbols in the stack. Now then you can reach the final state and stop the process. Okay. So this is the transition diagram representation of PDE. So here growing stack means what? We are going to push something into the stack. Okay, switch to the pop operation, next one. So and then pop the stack for matching symbols alone and then go to the acceptance state. As I told you, the particular string is accepted by the PDE. So and then coming to the second example. So here language of balanced parenthesis. Okay. So balanced parenthesis means in this we have the alphabet, two alphabet we have. That is one. First one is open parenthesis and then second one is the closed parenthesis. What about our stack symbol? We have Z0 on the top of the stack and then open parenthesis, closed parenthesis. In this we are going to use three states. Q0, Q1, Q2. So see the initial condition here, one arrow followed by the circle means which indicates the initial state. Okay, which indicates the initial state here. Now you have to draw the growing stack value. If it is open parenthesis, you have to push all the parentheses into the stack. If it is closed parenthesis, we have to pop out the top of the stack. That is matching parenthesis. One closing is equivalent to one open parenthesis. For one open, we have one closed parenthesis. Likewise, we can match the parenthesis here. Okay. So when we encounter a open parenthesis, we have to push it into the stack. If we read the closed parenthesis means we have to pop out the top of the stack. This is the condition here. So see the first rule here, current symbol is open parenthesis and then the stack is empty, then you can push it into the stack. Okay, and then current symbol is open parenthesis and then the top of the stack is, again I have open parenthesis in top, now again we need to push it into the stack. So this is the push operation, that is growing a stack. And then the next one, switch it into the next state. So we have close parenthesis. So as I told you, if we read the close parenthesis means and its equivalent open parenthesis should be pop out from the stack. Okay. So see, close parenthesis is the current input symbol And then the second symbol is the top of the stack. If it is close parenthesis and top of the stack, I have open parenthesis, means I have to pop it out. Okay. And then if it is epsilon, that means what? There is no parenthesis in my string, and then top of the stack is z0. You can reach the final state here. Pop the stack matching symbol, that is the second operation. So here also the same thing, that is for each close parenthesis we have to pop out one open parenthesis from the stack. Okay. So go to the acceptance state. Acceptance, otherwise final state. When you see the stack bottom symbol is Z0, and then we reach the final symbol. That means the end of the string, means we can reach the final state. Based on these two conditions, we can reach the final state. So what is epsilon, which indicates the end of the string? What about Z0? It indicates the empty stack. So there is no input symbol from the string, and then there is nothing that in the stack, then we can reach the final state. Therefore, the string is accepted by the machine. Okay, and then for this we can write the transition function also. So coming to the important concept in PDA, which is nothing but the ID. So what is ID? It is instantaneous description of PDA. Instantaneous description of PDA. So in finite automata, we studied extended transition function. Okay, extended transition function for DFA and then extended transition function for NFA. We already discussed in finite automata. So now coming to the next higher level PDA, here instead of extended transition function, we have to use the term instantaneous description. Okay, that is the major thing. So instead of extended transition function, here you have to use the new term, that is instantaneous description or ID. Okay. So see, a PDA has a configuration at any given instance. So we know that the configuration of PDA, right? Q is the state, W is the string, and Y is the top of the stack. So Q is nothing but the current state, W reminder of the input, that is unconsumed part, unreaded part of the given input string. Y is nothing but the current stack contents as a string from top to bottom of the stack. So we have the configuration, PDA configuration like this. Now you have to write the transition function. If the transition of q comma a comma x equal to p comma a, so this is the normal transition function of PDA, is a transition, then the following are also true. That is, this is the instantaneous description. The next 2 points, no, this is the instantaneous description. That is, current state comma a comma x means we are going to perform the pop-up operation. Okay, that is p comma epsilon comma a. And then the next one, q comma aw. What is a? A is the current, that is first symbol of the string, and then w is the remainder of the input. Okay, comma x comma b means the ID for this particular transition function is p comma w comma ab. So while writing the instantaneous description, no, we are using one symbol. This particular symbol is called a turnstile notation, which is used to represent the instantaneous description of PDA. Okay. And then next one, this instantaneous description, no, which is used to check whether the given string is a valid string for the given language. Okay, for this checking purpose, we are using ID, like our extended transition function in finite automata. So see here, all moves made by the non-deterministic PDA here. Q0 is the current state. These are all the input string, and then Z0 is the top of the stack. So this is the initial condition. So initially, we have 1 as the current input symbol. Okay, So if it is 1, we are going to push it into the stack so that the stack value is 1 is at 0. Okay. And then second is also 1 we have, again push it into the stack, push it into the stack likewise. Okay, WCW per R means divide this into two part. First part is the string and then the second half of the given string is a reverse of the first half. Okay, so first two values over no. In third value, from third value onwards, we need to perform the pop out operation. Okay, so see here green color, in green color we mentioned here performing the pop up operation on the second half of the string. And then next one, in PDA, there are two ways to accept the given string. There are two possible ways to accept the given string. The first one is accept by final state or accept by empty state. There are two types of PDAs that we can design those that accept by final state or accept by empty stack. There are two ways of acceptance of PDA. So here, PDAs that accept by final state. That is the first part. For a PDA P, the language accepted by P denoted by L of B by final state. So L is nothing but the language, P is the PDA. So this is the language for the given PDA by final state is see, W is what? It is a string. So within parenthesis, you have to mention the current state and then the current string and then Z 0. And then next one, Q, comma, epsilon, comma, A, which means such that the Q which belongs to the final state. What is capital F, which is the final state. This is the acceptance by final state. Acceptance by final state, you have to write the instantaneous description like this. So here the Q, it should be a final state. Okay. So after ID symbol, no, we have one state Q, which is the which should be a final state or any one of final state from the set of final states here. So here next one is acceptance by empty stack. That is PDAs that accept by empty stack here. For a PDA P, the language accepted by P denoted by N of P. So what is L of P? L of P means PDA accept by final state. N of P means PDA accept by empty stack. Okay, so here instead of writing epsilon in the middle, you have to write Z0 at the third parameter. That is the difference for acceptance by final state and acceptance by empty state. So this is PDF for our balanced parenthesis example. So in balanced parenthesis example, we have to perform the push operation for open parenthesis and reading each close parenthesis, we have to pop out one open parenthesis from the stack. That is the basic concept. And then this is for PF. So what is PF? It is nothing but the acceptance by final state here. So see, the diagram is same. That is from Q0, we have to form one self loop. Open parenthesis Z0 means you have to push. Open parenthesis means push. If it is closed parenthesis, we have to pop it out. So finally, reach the end of the string as well as the end of the empty stack. Then you can stop the process, which means we can reach the final state. Okay, so this is the PDA that accepts by final state. And then we have one more here, an equivalent PDA that accepts by empty stack. So first three functions are same. That is, if it is open parenthesis and then the top of the stack is at 0, now just push the operation. And then next perform the push operation. Second one also we have to perform the push operation. For each close parenthesis, we have to pop it out the open parenthesis from the stack. So what about the last one? So only we have change in the last step, that is there is no input symbol, which means end of the string, and then there is no top of the stack. Empty stack means we have to empty the stack. Okay, epsilon means what? Empty the stack. Therefore, we can reach the empty stack here. This is the equivalent PDA that accepts by empty stack. We have two ways of acceptance in PDA. First one is accepts by final state. Second one accepts by empty stack. So now PDAs accepting by final state and empty stack are equivalent. We have one question now. That is whether the PDA accepts by final state is equivalent to the PDA accepted by the empty stack. Okay, we have to check whether the equivalence of these two concepts, that is acceptance by final state and then acceptance by the empty stack. So see here, what is PF? PF is nothing but the PDA accepts by reaching the final state here, which means PDA accepting by final state. We have 7 parameters here, and then what about PN? PN means accepts by reaching the final, sorry, empty stack here. Accepting by empty stack, we have again same 5 parameters here. So Pn tends to Pf for every Pn that exists Pf such that L of Pf equal to L of Pn. Okay, so for every PDA accepts PDAs accepting by empty stack is equivalent to the PDA accepting by a final state. So vice versa also a possible here. And then this is the construction, that is Pn to Pf construction. What is N? Accepts by empty stack. F means accepts by final state. So whenever Pn stacks becomes empty, make Pf go to the final state without consuming any additional input symbol. Okay, whenever we reach the empty state, no, directly you have to draw one edge from that particular state to the end state without consuming any input symbol. So without consuming any input symbol means in that edges you have to write epsilon. So what is the purpose of epsilon? Without consuming any input, we need to reach the next statement. Simply we can use epsilon on the edge. Okay, so this is the construction from Pn to Pf. To deduct empty stack in P, Pf pushes a new stack symbol x0 initially before simulating Pn. So here, this is the diagram. That is, while we're reaching the empty stack, no, directly you have to draw one edge from current state to the final state with the input symbol epsilon. Okay, and then this is the example for parenthesis matching. First, we are writing it for n. What is Pn? Let us say PDA accepts by empty string. PDA accepts by empty string here. And then the next one, we are writing the transition function. So, and then the next, you have to write it for the stack, that is a final state. So we have only one change at the last step. Okay, so see that, see it in red color. It is the last state, last transition function we haven't changed. And then PF to PN construction for this particular parenthesis matching algorithm, parenthesis matching language. So PF means what? Final state, accepts by final state. Whenever PF reaches a final state, just make an epsilon transition into the new end state, clear out the stack and accept. Okay, this is the concept here. That is, whenever the PDA reaches a final state, just make an empty transition, that is null transition, and then make one new final state, and then clear out the stack and accept it. Okay, this is the second way of acceptance. Okay, whenever we reach the final state, we have to pop out, that is, clear the stack and accept the given string. So here we have one drawback, that is, what if PF design is such that It clears the stack midway without entering a final state. We have a question here, right? So to address this, add a new start symbol x0, not in the stack of PF. That is, we are going to add one new start state here. That is capital Q union P0 comma P. P0 is nothing but the new initial state, and then P is the new end state. We have to introduce two new states for this condition. And then we perform the same type of operation. So see here, P0 is the new initial state, and then we have to include one new final state PE. Equivalent, and then coming to the next topic, and then equivalence of PDA and CFG. So what is PDA? Push down automata. It is a mathematical model, and its equivalent language is context free language. Context free grammars are used to represent the context free languages. So what is grammar? It is nothing but a set of rules. So we have VTPS, 4 parameters context free grammar. First, capital V, which is nothing but the set of non-terminals, and then capital T, which is the set of terminals, and then what about P? P is nothing but the production or rules. Okay, so last one is the start symbol. Capital S is nothing but the start symbol. This is the general format of CFG. So here equivalence of PDA and CFG. Like our finite automata, no, we studied the equivalence of regular languages with finite automata. Likewise, here we have to see the equivalence of PDA and CFG. So in PDA, we have two different ways of acceptance, right? So PDA by final state, PDA by empty stack, we already discussed both are equivalent. Okay, that is equivalence of PDA by final state and the equivalence of PDA by empty stack we already discussed. And then this is equivalent to CFG. That is, we can construct CFG from the given PDA. Otherwise, we can construct PDA from the given context-free grammar. So that we can prove that the equivalence of CFG and PDA here. So first one, that is converting CFG into PDA. That is the first step. We are going to convert the given CFG into PDA here. So we have some input W and then PDA. Here we are taking the acceptance by empty stack. Acceptance by empty stack. What about the output of PDA? It may accept the given string or it may reject the given string. That is the output of the PDA. And then it implements the grammar. Okay, and then here the main idea is the PDA simulate the leftmost derivation on a given string. What is W? It is a given string. So in this, the PDA is push down automata, which simulates the leftmost derivation of the given string. So what is derivation? What is derivation? So at each and every step, the non-terminal is replaced by its production. Finally, we will get the string as the output. That is the derivation. Deriving a string from the start symbol. That is the derivation. Okay. So we have two different types of derivations here. First one is the leftmost derivation and then rightmost derivation. So what about leftmost derivation? Okay, at each step, no, the leftmost non-terminal is replaced by its production. That is the leftmost non-derivation. And then in rightmost derivation, at each step of derivation, the right-hand side, rightmost non-terminal, which is replaced by its production. So what is production here? Which is nothing but the rule. So the general form of this production is non-terminal followed by one arrow symbol and then the combination of terminals and non-terminals at the right hand side of the production. Okay, that is the production. So in this, the PDA, it simulates the leftmost derivation. So leftmost derivation at each step, the left side non-terminal, leftmost non-terminal is replaced by its production. So that the PDA, it can simulate only the leftmost derivation on the given input string W, and consuming it fully either arrives at acceptance or non-acceptance. Okay, so that is the output of PDA. If the given string is a valid string for the given language, then the string is accepted by our PDA. Otherwise, the string is rejected by our PDA. Okay, So according to the rule, what is rule? Production rule, it performs the operation. So and then converting, so see here we have the steps. Push the right hand side of the production onto the stack. What we have in right hand side of the production? So left hand side we have the non-terminals alone. Okay. For example, capital S tends to 0 S 0. Okay. So left hand side we have only S, capital S, non-terminal alone. In right hand side we have 0 S 0. Okay, we have to push the right hand side of the production onto the stack. Okay, with the leftmost symbol at the top of the stack. Okay, we have a leftmost symbol on the top of the stack. No, if we have capital S in the top of the stack, so instead of capital S, we have to push the right hand side of the production. Okay, so we have capital S in the top of the stack, means instead of capital S, I have to push 0 S 0. Okay, while performing the push operation for more than one symbol, we need to follow the direction from right to left. Okay, first you have to push the rightmost symbol, and then the next symbol from right to left we have to push. That is the first step. And then in second step, if stack top is the leftmost variable, then replace it by all its production. So in previous example, we discussed for WW for Arno, we have three different rules for the start symbol S. That is capital S tends to 0 as 0. Capital S tends to 1 as 1, otherwise capital S tends to epsilon. We have more number of rules for the leftmost non-terminal. So in left side we have only one symbol capital S, but in right side no, we have three different options for capital S. In this condition, okay, we have to replace it by all its production. Each possible substitution will represent a distinct path taken by the non-deterministic PDE. Okay. And then coming to the next one, if stack top as a terminal symbol. Okay, if top of the stack we have non-terminal, means instead of that non-terminal we can push its equivalent right hand side. No, if we have a terminal symbol on top of the stack, means what? If it matches with the current input symbol, we can pop it out from the stack. That is the operation. First step, we have to push the left hand side symbol into the stack. Okay. If it is a non-terminal, we have to replace by its production. That is pop out the non-terminal from the stack, and we have to push the equivalent value to the stack. Okay, if we have more than one option for the particular non-terminal, means we have to push all the possible ways into the stack. We have to push all possible production into the stack. Okay, and then if the top of the stack is a terminal symbol, and in the current string we have the same terminal, we just perform the pop operation. Okay, and then coming to the formal construction of PDA from CFG. We have CFG here. As I told, no, grammar is G is nothing but CFG. We have four parameters here. Capital V is a set of non-terminals. T is the set of terminals. P is the production. And then capital S is the start symbol. Okay. So this is the given production. Output, no, what about output? We are going to construct the PDA for the given CFG. So we have PDA as output here. So PN means was acceptance by empty stack here. So in curly braces, we have mentioned the set of states Q, and then T is the terminal, V union T is the stack symbol. Okay, and then we have transition function. Q is the initial state, S is the start symbol or final state. This is the output. Okay, initial stack symbol. So this is the transition function for all A, which belongs to the V. V is a non-terminals. Add the following transition into PDA. So we have to see here, capital A is the top of the stack, which is nothing but the non-terminal. So instead of that, we have a production capital A tends to small a. So we have to replace this particular non-terminal with the right hand side of the production. So in right hand side, we have only one symbol, small a. So we are replacing a with small a here. Okay, so see the stack before performing the transition, no, the top of the stack it contains capital A. After performing the transition function, no, instead of capital A, we can replace by its right hand side of the given production. So the right hand side we have small a. So we have to pop out the capital A and push the small a into the stack here. Okay, like this we can perform all the operations. So coming to the next one, CF2 PDA, we have one example here. So capital, here we have two different productions. Capital S tends to AS or epsilon. Capital A tends to 0 A1 and then A1 0 1. This is, we have two different options for capital S and then three different options for capital A. Okay, we have to write the productions here. So see the first one, this is for capital S alone. If capital S is on the top of the stack, then instead of capital S, I have to replace the right hand side of the production. So I have two options now. First, I have to write the first option, and then in second time, I have to write the second option. So see capital small q comma AS, because I have the production capital S tends to AS. And then the next one, Q comma epsilon, because I have the production capital S tends to epsilon. So likewise, you have to write the transition function for the second one, second non-terminal capital A. That is capital A, instead of I have to push 0, 1, 0 A1 into the stack. This is the first option. And then in second rule, I have A tends to A1, no. So instead of capital A, I have to replace A1. And third option, I have 0, 1 here. So instead of capital A, I have to push 0, 1 here. Okay, this is the construction of PDA from the given CFG. And then this is its equivalent transition diagram. If it is S, I have to push AS. If it is top of the stack is S, capital S, I have to replace it with its production epsilon. Likewise, I have to write the transition function in transition diagram. And then here for simulating a string 0011 on the new PDE. Okay, simulation of string now I have to write the instantaneous description here. So here the leftmost derivation of the particular string 0011. So I have to start with the start symbol. What is derivation? Deriving a given string from the start symbol, which is called as the derivation. Deriving a string from the start symbol. Okay. So here capital S is the start symbol. So for capital S, I have two different rules, AS otherwise epsilon. So here I have to use capital AS. So instead of capital AS, I have to replace 0A. Instead of A, I have the rule 0A1 because my string, it starts with a 0. No, I have to use the option with 0 is the first symbol here. Okay, 0A1 capital S. So likewise, this is the leftmost derivation. No? At each step, the leftmost non-terminal is replaced by its production. So finally, we will be getting the string 0011 here. Okay, and then see the operation, stack operation here. So initially we have to push the start symbol. So in second step, instead of capital S, I have the option AS. Okay, well, so here performing the push operation, no, we have to follow the rule from right to left. What is the rightmost symbol? Yes, first we have to push the S. After that we have to push capital A. So now the top of the stack is capital A. So instead of capital A, we used 0A1. Okay, so already we have S on the top of the stack, right? On the stack. So we have to push 0A1. While pushing, no, first you have to push 1, after that A, after that 0. That is right to left, we have to perform the push operation. So after that, the current input string, what is current input string? 0011. Okay, and then now check whether the current symbol and then the top of the stack both are 0. No, you just pop it out the terminal symbol from the stack. So likewise, finally we can reach the empty stack. Therefore, the given string is accepted by our PDA. Okay, and then the vice versa conversation, that is converting PDA into CFG, that is reverse engineer the production from transition. Here we are going to construct the production. What is production? It is a set of rules of our CFG. Okay, so this is bracket matching, which is nothing but the parenthesis matching example. And then we have the rule here. Okay, that is acceptance by empty stack is equivalent to, it's equivalent CFG. CFG means you have to write the rule, write the, see the right side. We have a newly introducing start symbol S tends to Q0, Z0, Q0. Okay, likewise you have to write the productions here. We have two different operations for Q0. Okay, so you have to write two different rules here, and then we have one epsilon. No, for that Q0 Z1 Q0 tends to E, Q0 Z0 Q0 tends to epsilon here. Okay, so instead of this left hand side is replaced with some non-terminals. Now I'm using capital A for this one. That is Q0 Z0 Q0 is replaced by capital A. Q0 Z1 Q0 is replaced by capital B. Okay, we have only two options here. So I'm using capital A comma capital B. Finally, after simplifying this, we will be getting S tends to B, small b capital B S, otherwise epsilon, small b capital B, otherwise E. Okay, this is the conversion of given PDA into CFG. So two ways to build a CFG. First, build a PDA, construct a CFG, or perform the derivation. Directly, you can derive the particular string from the given. Similarly, two ways to build a PDA: derive a CFG, construct a PDA, and then this is the indirect method, and then directly you can construct the PDF of the given language. And then we have two different PDS, deterministic and non-deterministic. The same way, non-deterministic means we have more than one path for a specific input symbol. If it is a deterministic, we have only one path. Okay, and then here WCW per R, the same language, but we have one separator symbol in between the string and its reverse. We have C here. Okay, so in this type of language, no, first you have to push all the string up to C into the stack. While reading the C, no, we no need to perform any operation on stack. Okay, no need to push or no need to pop it out for C alone. So after C, we are having a reverse of the string. So for reverse of the string, no, we have to pop out the stack. So W, we have to push. For C, no need to do anything. For W per R, we have to perform the pop operation. Okay. And then this is the definition of deterministic PDA. A PDA is deterministic if and only if the transition function has at most one member for any A. Yeah, as I told, no, only one member. We have one member. At most one member, na, we have only one member here. If it is non-deterministic, na, we have more than one member for any small a belongs to the alphabet. That is non-deterministic. So here PDA, DPDA versus regular languages. Okay, regular language is the innermost part of anything. After that, we have DPDA, and then after that, we have NPDA. So finally, we have the summary here. So in today's class, we discussed PDA, CFL, what is CFL, context-free language, and then context-free grammar. And then we have two ways of acceptance of PDA, that is acceptance by finite state, acceptance by empty stack. And then we discussed the instantaneous description and the transition diagram of PDA. After that, we discussed about the conversion, that is from CFG to PDA and PDA to CFG. Okay. And then here we have only one gate question. Identify the language generated by the following grammar. So here we have the grammar. So using this grammar, we have to derive a string. Whether you can use a rightmost derivation or leftmost derivation, we have to derive one string. So after deriving a end string, we have to recognize the string. Okay, with based on the recognition, we can write the language. So according to the given rule, we will be getting a power m, b power n as the language, where n it should be greater than m, where m is greater than or equal to 0. So this is the given. This is the language for the given CFG. Okay.
So that's all about today's class, students. So kindly work out more examples. Okay, more examples on PDA and CFG. Okay, so we'll be meeting in the next class. Thank you so much.